Everyone, let's catch up quickly with this topic, minimum continuous thermal flow. Why every pump has a flow, it must never run below. So, it's simply the minimum flow that must continuously pass through the pump to remove the heat generated inside it and keep the pump operating safely. Think of it like drinking water on a hot summer day. Your body can survive without enough water, but it definitely will not perform well. The same is true for a pump. Running below its minimum thermal flow may not stop it immediately, but over time you are reducing its health, reliability, and lifespan. We have all met that one person who says, the pump is running so everything is fine. Well, that's like saying the car's engine is running so it doesn't need a radiator. A pump can be running and still be quietly damaging itself. Let's break down the terms. Minimum, which means the lowest flow rate the pump can safely handle. Continuous means not just for a moment but a sustained operation. Thermal, the limit is set by heat buildup in the fluid. Flow, it means the liquid moving through the pump carrying heat away. Let's see how a pump can get damaged. First, understand what happens to the energy entering a pump. The motor rotates the pump shaft and supplying input energy to the pump. Now here is something many people don't realize. Not all of this input energy becomes useful pumping energy. A part of it is converted into useful output energy that moves the liquid by increasing its pressure and flow. But the remaining energy doesn't seemingly disappear. It gets lost inside and around the pump, and according to the law of conservation of energy, we all know that energy can never be destroyed. It can only be changes its form, like it can only be transformed from one form to another form. So those losses are mostly converted into heat. The more losses we have, the more heat is generated inside the pump. Now let's see what happens inside the pump. These are called internal losses because they occur within the pump casing itself. The first is friction loss. As the impeller rotates, the liquid continuously rubs against the impeller surfaces, casing and passages. This friction converts part of the mechanical energy into heat, just like we rub our palms and the heat is generated. The second is internal recirculation. Instead of all the liquid moving toward the outlet, a small portion leaks backward through clearances inside the pump. This liquid keeps circulating inside the pump without doing any useful work. The pump still spends energy moving it, but no useful output is produced. That wasted energy again becomes heat. So internal losses don't help pump the liquid. They simply increase the pump's temperature. Now let's move outside the pump. These are called external losses. As you can see, even before all the motor power reaches the liquid, some energy is already lost. For example, the shaft seal creates friction while preventing leakage. The bearings also create friction as they support the rotating shaft. These parts are essential for the pump to operate, but they also consume a small amount of energy. Once again, that energy isn't destroyed. It is converted into heat. So when we combine internal losses and external losses, a significant amount of heat is continuously generated inside the pump. Now imagine cooking pasta. You leave the gas on, but there is barely any water in the pot. So the water heats up much faster and eventually things start burning. A pump behaves in a surprisingly similar way. The liquid flowing through the pump isn't only being transported, it is also acting as the cooling medium. It absorbs the heat generated by all these internal and external losses and carries that heat out of the pump. Now imagine someone says, let's reduce the flow, it will save energy. Sounds logical, but not practical. Less liquid means less cooling. The heat has nowhere to go. Temperatures begin to rise and seals wear faster. Bearings suffer, efficiency drops, and suddenly the maintenance department has a new project they never asked for. As you can see, I have also mentioned this in the PPT. Flow drops means pump runs near shutoff and the heat concentrates, temperature rises, which eventually causes the damage, which is vaporization, like the water boils and it creates the vapor. It creates the water bubbles which implodes and causes cavitation, and also it causes vibration. So that's why engineers define something called minimum continuous thermal flow. Now you could spend your time digging through formulas and manuals, or you could let Capacira do the heavy lifting while you focus on engineering decisions. Enter your operating conditions, review the results in seconds. Because engineers are hired to solve problems, not to find the same thing over and over again. Visit Capacira, explore it yourself, and see how much simpler engineering can be. Capacira, engineering made faster, decisions made smarter.